In this episode, we're going to focus on a part of OT that often looks familiar to beginners because it involves computers, screens, and files, but it behaves differently than office computing because it is tied directly to industrial operations. OT workstations and data systems are where people design, control logic, monitor processes, respond to alarms, review trends, and coordinate maintenance and quality decisions. If you only think of OT as sensors and controllers, you miss an important layer where humans and data meet the physical process. This layer matters because it is where decisions are made, where mistakes can be introduced, and where visibility can be gained or lost. It also matters because these systems often run software that looks like normal desktop software, but the consequences of disruption can be larger than losing a spreadsheet. For the exam, you need to be able to classify common workstation roles and common data systems so you can understand why access is restricted, why certain updates are delayed, and why some devices are treated as high risk even though they look like ordinary computers. Once you can name the roles and explain what they do, OT scenarios become much easier to interpret. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. An operator workstation is usually the frontline interface for running the process, and it is closely tied to the human-machine interface function you learned earlier. Operators use these systems to watch process status, acknowledge alarms, adjust set points within approved ranges, and respond to abnormal conditions. The goal of an operator workstation is not creativity. It is stable, reliable operation, often across long shifts, with clear displays and predictable behavior. That means operator workstations are often locked down in ways that would feel restrictive in an office, because reliability and consistency are valued over customization. If an operator workstation crashes, becomes sluggish, or displays wrong information, the operator's ability to maintain safe control is reduced. That makes these workstations safety relevant, even if they are just computers at a glance. Operators may rely on trends, alarm summaries, and graphical views of the process, and those views shape their decisions under pressure. From a security perspective, operator workstations are sensitive because they can be used to issue commands, and because they influence what operators believe is happening. Protecting integrity, availability, and appropriate access is critical because a wrong display can be as dangerous as a wrong control action. Engineer workstations serve a different purpose, and that purpose makes them both powerful and risky. Engineers use these systems to develop, modify, and deploy control logic, configure devices, tune control loops, and manage how the system behaves. In many environments, the engineer workstation is the place where changes originate, meaning it can influence controllers, HMIs, and sometimes the broader control network configuration. Engineers may use specialized software that connects to PLCs, distributed control platforms, or supervisory systems, and they may perform updates, backups, and restoration activities. Because engineer workstations are used for design and change, they often require higher privileges and deeper access than operator workstations. That higher access makes them a prime concern for security, because a compromised engineer workstation could become a pathway for unauthorized changes that affect the process. Another operational constraint is that engineering activities must be coordinated, tested, and controlled, because changes can have unintended consequences. A beginner should understand that engineer workstations are not equivalent to developer laptops in IT, because the code they handle can directly change physical outcomes. A useful way to differentiate operator and engineer systems is to focus on decision type. Operators make real-time operational decisions within established boundaries, often responding to alarms and maintaining stability, while engineers make structural decisions that change boundaries, logic, and system behavior over time. That difference affects how each system is managed, who can use it, and what normal activity looks like. An operator workstation might allow set point changes but not logic changes, and it might restrict installations and removable media. An engineer workstation might have access to configuration tools but should be used under strict change control and monitoring. This difference also affects the risk of accidental harm. A tired operator can make a wrong adjustment if the display is confusing, while an engineer can introduce a hidden logic error that causes intermittent failures weeks later. Security controls should reflect these realities, focusing not only on preventing attackers, but also on reducing the chance of costly mistakes. For exam thinking, when you see a scenario describing logic downloads, configuration changes, or tuning, you should immediately think engineer workstation role. And when you see a scenario describing alarms, monitoring, and routine adjustments, you should think operator workstation role. Classification is about matching function to context. Historians are a special class of OT data system that collect and store process data over time, turning real-time signals into a record you can analyze. A historian is not just a database in the office sense, because it is designed to handle time series data, meaning measurements that change over time, like temperature readings every second or valve positions every few milliseconds. Historians support trend analysis, root cause investigation, performance optimization, and reporting, and they help teams answer questions like what happened before an alarm, how often a pump cycles, or whether a process is drifting out of spec. Because historians store a memory of the process, they can be essential during incidents, whether the incident is a safety event, an equipment failure, or a suspected security issue. Integrity matters because if historian data is altered, investigations can be misled, and decision-making can be based on false patterns. Availability also matters because many teams use historian data for daily operations and planning, and losing that visibility can slow recovery and increase uncertainty. Historians also create connectivity questions because they often receive data from control networks and may share data with business systems for reporting, which introduces convergence risk. Understanding historians helps you see that OT security is not only about control, it is also about trustworthy records. Another category to understand is portable systems, because they are common in OT and they introduce unique risks. Portables can include laptops used by maintenance technicians, vendor support devices, diagnostic tools, and sometimes tablets used for inspections or configuration. These devices are attractive in OT because they allow work to be done at the equipment, especially in large facilities, and they can carry specialized software needed for troubleshooting. The challenge is that portable devices move between zones, between systems, and sometimes between organizations, which increases the chance of bringing unwanted software or risky configurations into sensitive areas. A portable may be connected briefly to a controller network, then later connected to an office network, and that bridging behavior can bypass intended boundaries if not managed carefully. Physical security is also harder because a portable can be lost, stolen, or left unattended, and it may carry credentials, configuration files, or sensitive process information. Another operational constraint is that portables are often used under time pressure during outages or urgent troubleshooting, which increases the temptation to skip checks. For exam reasoning, when you hear about a laptop being plugged in for diagnostics or a contractor device being introduced, you should think portable risk, boundary crossing, and the need for controlled procedures. Portables can be valuable tools, but they are also common paths for accidental introduction of malware or misconfiguration. It also helps to understand that some OT environments have specialized workstations that support particular operational roles, even if the exam uses broad categories. For example, there may be quality systems that track process parameters and product results, maintenance management systems that coordinate work orders, or asset management systems that track device configurations and lifecycle. These systems may interact with OT data and sometimes with OT networks, creating both value and risk. The key beginner point is that any system that influences operations, stores operational records, or connects into the control environment should be considered part of the OT ecosystem, even if it looks like a normal server or PC. Classification is not about whether the device has a rugged case. It is about what it touches and what decisions it supports. A system that only prints reports may be less critical than a system that is used to change control logic, even if both run on similar hardware. In OT, criticality is tied to process impact, not to how modern the device looks. That is why a simple workstation can be treated as mission-critical when it is part of safe operations. A big concept tied to these systems is access and privilege, because different roles need different capabilities. Operators typically need enough access to run the process, respond to alarms, and adjust within limits, while engineers need access to make plan changes, perform troubleshooting, and manage configurations. Historians need access to receive data from many sources, but they should not necessarily have the ability to send control commands back into the process. Portables may need temporary access, but temporary access must still be governed, logged, and constrained to reduce risk. Beginners sometimes assume that giving broader access makes things easier, but in OT, broader access often creates more risk without adding real value. The goal is to give each role what it needs and no more, and to ensure that actions are attributable so that if something goes wrong, the team can understand what happened. Attribution matters because OT incidents can be complex, and the difference between a mistake and a malicious act may depend on log evidence. Workstations and data systems are also where credentials are used, which makes them central to identity and access control decisions. When you classify these systems, you are also indirectly classifying who should be allowed to do what. Another important concept is availability and stability, because workstations and data systems in OT often need to be more stable than their office counterparts. In an office, a workstation crashing might be annoying, but in OT, a workstation crash can reduce visibility during a critical moment. That is why OT environments often restrict changes, use stable configurations, and avoid unnecessary software installations. It is also why patching and updates can be handled differently, with more testing and scheduling, because untested changes can create unpredictable behavior. A historian system, for example, might be relied upon for both operational monitoring and post-event analysis, so its stability and storage integrity are important. A portable device used for troubleshooting might need specific drivers or software versions to work correctly with older controllers, and changing those versions can break compatibility. Beginners should learn that stability is a form of safety because stable systems support predictable operations and reliable response. This does not mean never updating, but it does mean updating with intention and coordination. Many exam scenarios test whether you respect this stability requirement when choosing actions. Data flow is another reason classification matters, because each type of system tends to sit at a particular point in how information moves. Operator workstations are close to real-time control and display. Engineer workstations are close to configuration and change. Historians are close to collection and analysis, and portables often act as temporary connectors. When you can picture data flow, you can identify where monitoring should occur and where boundaries should be strongest. For example, a historian might receive data from control networks and then share curated data outward for reporting, which creates a boundary where security controls should be thoughtful. An engineer workstation might connect to controllers for programming, which creates a high-risk path that should be tightly controlled and used only when needed. An operator workstation might be connected to supervisory systems and should be protected from unnecessary external access because it supports real-time decisions. Portables may connect to multiple segments and therefore should be managed with extra care because they can carry issues from one zone to another. Data flow thinking is a beginner-friendly way to understand segmentation without needing to memorize complex architectures. You simply ask, where does data come from? Where does it go? And what would happen if it was wrong or unavailable? A common misconception is that because these systems look like computers, they can be secured exactly like office computers with the same tools and the same aggressive policies. In reality, OT constraints can make some tools risky, such as heavy scanning or frequent forced updates, because they can interfere with timing, stability, or compatibility. Another misconception is that historians are not important because they do not control the process, but historians can influence decision-making and incident investigation, and losing trustworthy history can increase both operational and security risk. Beginners also sometimes assume that a portable device is safer because it is not always connected, but movement and intermittent connection can increase risk because it can bypass monitoring and introduce unknown software. There is also a misconception that the most important systems are always the newest ones, but many critical OT workstations run older software because it is the supported version for the control platform, and that reality shapes how security must be applied. The correct mindset is not to judge the environment, but to understand it, because understanding leads to safer, more effective protections. The exam rewards that understanding by presenting scenarios where the best choice respects both security goals and operational constraints. To close, classifying OT workstations and data systems is a core skill because it helps you understand who does what data is trusted, where changes originate, and where boundaries matter. Operator workstations support real-time monitoring and safe process decisions. Engineer workstations support design and controlled change. Historians store time series records that support both operations and investigations, and portables provide flexibility while introducing boundary-crossing risk. These systems may look like familiar computers, but their roles tie them directly to physical outcomes, which makes stability, integrity, and controlled access especially important. When you can identify each system's purpose and place in the data flow, you can reason through exam questions that ask about responsibilities, constraints, and safe choices. This also sets you up for later topics, because network types, protocol choices, and security controls make more sense when you understand what kinds of endpoints exist and why they matter. If you keep your focus on function and impact, the OT environment becomes a coherent system instead of a confusing collection of devices.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.